Hello everybody, this is going to be the iodine clock reaction lab. So what we're measuring in this one is the reaction of hydrogen peroxide with iodide to form iodine. Okay, and so we're going to be measuring how the concentration of this changes over time. We're going to do this with concentrations raised to powers that are the orders times a constant. Okay, so there's also going to be a temperature dependence, and we're going to determine this by using the Arrhenius equation. Okay, so there's going to be two main type of equations that are going on in here. In this experiment, we're going to calculate the reaction orders, and we're going to talk about the temperature effects. So we're going to make up 6 different solutions and measure how fast these reactions happen in each of these different solutions. So we're going to start with reaction mixture 1. So we're going to start out with 15 milliliters of water. As you will, if you followed along with the table that was just flashed up there, it'll tell you how much concentration, how much volume of everything you should be having into your sample. So after the water, we come with the buffer, which is 6 milliliters of our buffer. Okay, this is just going to make sure that we know that the pH isn't changing. Okay, so we're making up this solution with the exact same amounts of stuff, or one variable at a time, so that we can measure how fast the reaction happens in different parts. And remember, rates are all about how fast. So that's what we're trying to do. This is the iodine clock reaction is kind of a very famous reaction that you can visibly see when the reaction happens, and it is a clear color change as you're going to see. So we started out with 15 milliliters of water. We now added 6 milliliters of buffer. So on our table of all of the stuff that goes into the solution, next one would have been acetate, but it's 0 for this solution. So the next one after that is potassium iodide, in which case we need 5 milliliters of 0.05 molar potassium iodide solution. So this is the I minus that is going to turn into I2 or iodine when the reaction actually completes. So we need a good amount of I minus in the solution. So we measure out our 5 milliliters and we dump that in the solution too. Okay, so if we're going along our columns in that reaction order calculation table, next thing in the list is starch, so 0.1% starch solution. So the starch really has nothing to do with the reaction. It's just there because so when we add starch to any solution that contains I2 or iodine, it's going to turn a bluish color. So right now we've added the starch to iodide or I minus. It does not turn blue, so that's good. So then our final component that we're going to add in here is the Na2S2O3, or the persulfate, or thiosulfate, sorry. So in this case, this is going to be the thing that prevents our reaction from turning blue. Okay, so this stuff, its sole purpose is to keep the reaction from happening right away. Okay, so now we've got our solution all made, we check our temperature. In this case, it's 21.5 degrees in the room when we're doing this. So then final component of this is the hydrogen peroxide. So hydrogen peroxide is what's actually going to start this reaction. It's the only thing we haven't added to our reaction solution yet. We measure that out, we keep it separate because as soon as we mix the stuff in the beaker with the hydrogen peroxide, we have to start. Okay, so we measure everything out, we got everything all set. Now we get our timer started, we start our timer, and we dump it. So this is how we're doing our measurement, it's how long it takes. So dump, start, and now the reaction should be happening. So what's happening here is our H2O2 is trying to turn the I minus into I2. But that Na2S2O3, the thiosulfate that we had in there, it's trying to make everything, it's trying to take all of the iodine and turn it back into I minus. So it's stopping the reaction from happening. So as long as there's the S2O3 or the Na2S2O3 in the reaction, it's not going to change color. But as soon as that runs out, it's going to change color. So how long that takes is what we're measuring. And so now you can see in the reaction, we're up to pretty much a minute, and we haven't seen any color change whatsoever. It is still nice and crystal clear. So at this point, there's still this Na2S2O3 that's causing the reaction to go back and kind of not turn blue. And so we're measuring how long it's going to take for all of that to be used up. And then as soon as it's used up, the hydrogen peroxide will turn the I- into I2 and it'll turn blue. Okay, so again, this is kind of the reaction and how it goes. You just start it and you just have to look at it and pay close attention until you see that color change. And it can take a while. Once you finally do a couple of them, you start to see what the time correlation is and you get an idea as to how long it's going to take. But at the beginning, you just look at it forever until you figure out when it's going to change color. So we should see blue color. That's why we put it on the white paper. Okay, so we're going to do this for all the different combinations of concentrations that we have in that table, in the reaction order calculation table that you saw just before we started making up the solution in the videos. And we measure out how long it takes to turn blue. And that's this lab. So knowing what the concentrations of everything is and how long it takes to turn blue, that's all of the stuff we need for our calculations. We need concentrations of everything, and we need our actual times, and that'll get us our rates. So you can see here we're up to a little over 2.5 minutes, and there is the blue color. And so you can see the color change. That would be when you call the stop, and we would record that number. So once we've got all of these times and all of the concentrations, so we have to turn all of those volumes into concentrations, just like you do in this table here. You can start doing the calculations for figuring out what the order is for everything. So we have a rate law for this. Rate is equal to K times the hydrogen peroxide concentration to the X, I- concentration to the Y, and H3O concentration to the Z. So in this case, we have to do 3 different sets of these reactions. Each one, we try and keep 2 of the concentrations the same. So in this one, we're measuring I-, the H2O2 and the H3O, they're both the same concentration, so those don't get any play into this. And so then we have to do everything from there. So we work this out and we figure out what the order is, or does the amount of time it takes change if we change the concentration of one thing only. And we figure out what the order of everything is in this reaction. In this example case, you'll see that the reaction is first order for H2O2, first order for I-, and so we end up with a second order reaction. Okay, so now we're going to do effective temperature. We need things in terms of rates, so you need to calculate what the rate is. The rate is dependent upon the amount of S2O3 that's in the reaction. And so we know what the amount of S2O3, the Na2S2O3 is, so we can figure out what the rates are from that, as you can see in that previous one. We're going to make another graph of the ln of K over 1 over temperature, which is very like the graph that we made in a couple labs ago, except for this one uses temperature instead of pressure. Okay, so the data for this is collected by doing the same reaction with the same solutions at different temperatures. So we had one that was up in the 40 degrees, another one that's at 10 degrees. So we have high temperature and a lower temperature, but they're both the same concentrations for everything. So concentration of our reactants can change how fast our reaction goes, but we can also change how fast our reaction goes with temperature. So previously when we did our table, the reaction mixtures 1 through 4 were all at the same temperature, but when we do the reaction at different temperatures, we're also going to get different times. So in this case, we pour in our hydrogen peroxide into our 2 reactions. The warm reaction started a little later, but close enough. And so now we just count again. And so last time it took over 2 minutes for the reaction to change color, but we've got the warm temperature one, and we assume that the warm temperature one is going to change color faster. And in fact, if you look real closely right now, it's actually changing color as we speak. Right now, it's kind of a yellowish, brownish color. And so that one's already done. Okay, so the warm temperature one took less than a minute. It's only like 40 minutes, 40 seconds or so on the clock. And so that one went faster because it was warmer. And so now we're going to see, well, how much slower does the one that's colder? So the warmer one was at 40 something degrees. Okay, so that one was quite a bit warmer. It's over 10 degrees warmer than what we did at the beginning, which was around 22, 21. Okay, so the colder one's at 10. Okay, so that's over 10 degrees colder. All right, so then we have to figure out how long does that one take. So our normal room temperature reaction took over 2 minutes. And so we can be pretty sure that the one that's colder is going to take longer. It's just that you never can tell if it's going to be you have to measure it out. So is this a linear relationship? Is it a logarithmic relationship? Something like that is what we're looking for in this. So while this one changes color, we just have to wait and see how long it's going to take. You guys are going to would be doing all these reactions yourself for all of the solutions, 1 through 6 that are listed in the table that we saw before. You'd make them all up. You'd then afterwards calculate out what the concentration of all of the relevant things are in each of the solutions. And so concentrations are going to be variable because each one of these solutions is meant to test a different concentration or different thing. So those are the things that we're changing. So we want to calculate the concentrations of everything because our original table only shows us the amounts, the volumes in milliliters that we added in there. So we calculate everything out into concentrations in moles per liter that we have in the solutions. We can then use those to figure out what the rate of the reaction is when we have the time to go along with it. That's going to be from the amount of S2O3 that's in each of the reactions and how long it takes. And then we're going to use those rates and the temperatures that we have in here to do our Arrhenius plot and figure out what the temperature dependence is. So what's the slope of the line that goes through the points for this? So we know that warm temperature equals fast, cold temperature equals slow. That's kind of a known thing that we do with any type of common sense sort of reaction. It's not always the case. There are some things that go faster when they're colder and slower when they're warmer, but most things go faster when they're warmer and slower when they're colder. But we do have to measure out what the coefficient is, how much faster it gets when it gets warmer, and all of that, because you want to know how much you have to heat it up to get it to go as fast as you need. Remember that this is all towards more of a chemistry standpoint of, okay, so say we wanted to scale this up for an industrial reaction. Well, heating up a reaction makes it go faster, but it also costs us more money because if you have thousands of liters of reaction, heating up that water or that solution isn't cheap and it isn't free. And so if we heat it up 5 degrees and that does what we need, good enough. We can save the money on trying to heat it up the extra 10 degrees. We also don't want it to go too fast. If it goes too fast, it could be bad then too. All right, so here's the data that you're going to use. So it's all the same reaction mixtures, label 1 through 6, but now we've got different times and temperatures that go along with them. So you're going to use this data to actually calculate what we're going to ask in the post-lab quiz, along with the same volumes and concentrations of things that were in the examples. All right, so you've got the data, you've got all the concentrations and stuff. That should be all you need to answer the questions in the post-lab quiz. But make sure you've got concentrations, rates, and the times all prepared before you start the quiz.